Good afternoon, students. Today I'm here to present to you the fifth lecture dedicated to growth of nanocrystals. Diffusion-controlled growth from a supersaturated solid solution has three stages. First one, nucleation. Second one, normal growth, or growth on the account of the dissolved matter. And the third one is the competitive growth, which is also called coalescence. In general case, the phase transition at constant temperature proceeds between a supersaturated vapor of N monomers or molecules and droplets containing IN monomers. The rate equation determines the N, the number of the monomers inside of the droplet or cluster. It is also the difference between the gains and the losses, where the size of the cluster changes by the gain or the loss of one monomer. One of the most famous models for growth is Lifshitz-Lozov model. It is also widely used to calculate the growth of semiconductor nanocrystals inside of the dielectric matrices. So that's why we will use it in our further discussion. The first stage is the nucleation, which means the formation of a very big number of small nucleus. Here we have the very beginning of our growth process. That's why we can consider the concentration of ions that will be used in our third future crystals as constant one. The nucleation rate, or the velocity of forming of new nucleus, can be written in this expression. Here delta GA is the activation energy, which is associated with jumps of atoms across the interface between matrix and the nucleus. Sigma is the interface free energy per unit area, and A asterisk is the critical radius here. The radius distribution of nucleus obey the Gaussian function at this stage. The number of nuclei and the critical radius are controlled by the supersaturation rate. The larger the supersaturation, the smaller the critical radius is, and the smaller clusters can grow. At normal growth stage, the number of nucleus are considered to be constant. They have all grown during previous stage. Now they have stopped. Whereas the concentration of ions distributed in the matrix decreases monotonically. The Lifshitz-Lozov model assumes that the transport of atoms to the cluster surface is realized by diffusion in the supersaturated solution. That is why the monomer distribution in time and space is obtained from the diffusion equation, this one. Here D is the diffusion coefficient, delta is the supersaturation, that is the difference between the concentration of the saturated solution at the equilibrium and the average concentration of the supersaturated solution. The critical droplet radius at this stage is defined by this equation. Also, common for both nucleation and normal growth stages is a steady growth of the total mass of the semiconductor phase. Here we have that really supersaturation is a function of time, and at every supersaturation value we have such value of critical radius at which the cluster is in equilibrium with the solution. If a cluster has a radius more than critical radius, the cluster will grow. If the cluster has the radius smaller than the critical one, then the cluster will dissolve. Smaller cluster is unstable because the concentration around it is too high. Larger cluster is unstable because of the depletion region around it with small concentration of ions. And so the monomers feel the concentration gradient driving the diffusion of the matter from small particles to larger particles. And a diffusion-controlled competitive growth of nanocrystals is a result of this. According to the theory, at this stage, no excessive ions exist in matrix anymore, and the total mass of the semiconductor phase is considered to be constant. Under these conditions, the surface tension becomes very important. A decrease in the surface between a crystallite and a matrix gives rise to a decrease in the free energy of the system. It means that growth dynamics is now by a diffusive mass transfer, and critical radius separates crystallites into two groups, either for further growth or for dissolution. The size distribution function, which is also called a Lifshitz-Losev function after the name of creators, have this look, and it looks like here on the picture. Lifshitz-Losev function is asymmetric with respect to the mean crystal size. Here the maximum is situated at about 1.2, and the width of this function is about 0.3. The slope to the larger sizes is abrupt. That's why the nanocrystals of sizes larger than twice the critical radius cannot exist. The time dependence of mean radius at this stage obeys a cubic law by these equations. This means that the number of crystallites decreases as the time in -1 degree. But in real systems, we have such a situation when various stages may coexist, in particular nucleation stage and normal growth stage. Here we have that the number of nuclears is no longer constant, so they appear during a whole growth process. And the time dependence of the mean radius, in this case, has a very complex shape. In the initial stage, it is close to the parabolic law as in a normal growth stage, whereas the final stage here follows the cubic dependence as in coalescence stage. But there is also an interval between these two stages where the size distribution changes its form from Gaussian form to Lifshitz-Losev form, and also here the mean size remains constant. But during production of semiconductor nanoparticles or nanocrystals inside of a commercial glass, usually a two-step procedure takes place. At the first step, low temperature and long duration is usually used to provide a nucleation of big amount of small nucleus. At the second step, high temperature and short duration are usually used to provide intensive growth of the nanocrystals of nucleus without changing the concentration. The two-step regime provides a better control of size, of distribution, and of concentration of nanocrystals inside of the glass matrix. That's why, namely, two-step procedure is usually used in the commercial glasses. For example, color cutoff glass filter production and photochromic glasses production. Thank you for your attention.